Let's begin by looking at a selection of short rate models. We start with the oldest model, the Vasicek model, dating back to 1977, which has the following dynamics. Here, kappa, mu and sigma are constants, and kappa is strictly positive. The drift term here shows that the short rate has mean reversion. For example, if r is less than mu, then the drift is positive, and therefore the short rate drifts upwards. On the other hand, if r is greater than mu, then the drift is negative, and therefore the short rate will drift downwards. It follows that the short rate mean reverts to the level mu. The rate of mean reversion is determined by kappa. If kappa is large, then the short rate will mean revert very quickly, whereas if it's small, it will mean revert quite slowly. If kappa is negative, then the short rate would be repelled from mu. The next model we consider is the Cox-Ingersoll-Ross model, or CIR model, which dates to 1985 and is also quite popular. It has the following dynamics. Here kappa, mu and sigma are constant again, with kappa strictly greater than 0. And as for the Vasicek model, we have mean reversion. Notice, however, that we have the presence of a square root term here. And it can be shown that the short rate can never be negative, so this square root will never give you any problems. Next, we consider the Dothan or a Randleman-Barter model with the following dynamics, which, as you can see, is just geometric Brownian motion. Here A and sigma are constants. The Merton model is just an arithmetic Brownian motion, again with constants A and sigma. The Holy model is a modification of the Merton model, which has a time-dependent drift. Notice that the other models on this slide have very few parameters. Vasicek and CIR each have 3 parameters, and Dothan and Merton both have 2 parameters. As such, these models are not sufficiently flexible to fit the entire observed term structure of bond prices. This is mitigated if we use essentially infinitely many values, namely theta t for every value of t, and this will allow us to fit the entire observed term structure. Notice that the Vasicek, Merton and Holy models have short rates that are Gaussian and therefore can go negative. The Dothan model is log normal and therefore will have a short rate that is strictly positive. And as we already mentioned, the CIR model also has non-negative rates. Now we can repeat the trick of replacing a parameter by a function and obtain the Hull-White versions that extend the Vasicek model, where the mean reversion rate becomes time-dependent as well as possibly the volatility. Similarly for the Hull-White extended CIR model, or for a similar extension of the Dothan model called the Black-Derman-Toy model, and a slightly different approach to assure non-negative rates is to model instead of the short rate, the log of the short rate, which yields the Black-Karaszynski model, given as follows. All of the above models can be written in the following form. Let's now consider models where the short rate is log normally distributed. Examples of those, as we've seen, are the Dothan and Randleman-Barter model, the Black-Derman-Toy, and also the Black-Karaszynski model. All of these yield log normal short rate dynamics. And all suffer from the following problem. Suppose that A denotes the riskless bank account with the usual dynamics. Then the expected value of the bank account can be approximated as follows. Here we approximate this integral inside the exponential using the trapezoidal rule for integration with just one trapezium, and we can do that if t is sufficiently small. Then, since r0 is known, we can take out this exponential here and manipulate the expression involving RT to obtain the following. Now, since RT is log normally distributed, the exponent here, ln t over 2 plus ln RT, is normally distributed. And so we have an expectation here, which is of the following form, where Z is normally distributed. Now, if we were to compute this expectation using the density function of a normally distributed random variable, we'd have an integral that has the following form, modulo some constants. As e to the z is much larger than e to the z squared over 2, this integral is infinite. And thus the expected value of the bank account is equal to infinity even if t is very small, i.e. the bank account on average explodes. Similarly, it can be shown that the expectation of 1 over the price of a zero coupon bond is equal to infinity for all t strictly greater than 0, but of course strictly less than capital T. One consequence of this so-called log-normal explosion is that one cannot price euro-dollar futures, which are a very heavily traded interest rate derivative. The problem with log-normally distributed short rates goes away if we assume that instead of continuous compounding, we have discrete compounding. This is important because the Black 76 formulas for caps and swaptions assume that the LIBOR rates and the swap rates are log-normally distributed. We'll spend some time on developing log-normal models of discretely compounded rates later on. Let's now consider fitting or calibrating our models to the observed term structure of zero coupon bond prices. This is also known as inverting the yield curve. In our current setup, the bank account is the only primitive security, and in such a case, every probability measure which is equivalent to the objective measure is a risk-neutral measure. This is because all discounted asset prices are martingales under any measure, since the only discounted primitive asset is the bank account divided by itself. As this is equal to 1, this is a martingale under any measure. So we are in a very incomplete market setup, where the only random variable that can be replicated with the bank account is the bank account itself. Now, given a short rate RT and some process lambda, which is a function of time in RT, it is possible to define a new measure Q lambda as follows. If we then define zero coupon bond prices by the following expectation under the measure Q lambda that we have just defined, then we have an arbitrage-free term structure model. It therefore follows that there are many risk-neutral measures, i.e., as we have said, our model is incomplete. However, zero coupon bond prices are traded in the market, and we cannot just accept any arbitrary value for the prices of zero coupon bonds. They must fit what we observe in the market. So by calibrating this function lambda to observed zero coupon bond prices, the correct lambda and risk-neutral measure can be found, i.e. the risk-neutral measure that is used by the market to price. Now it is very common to model the short rate directly under the risk-neutral measure, i.e. to posit some dynamics of the following form under the risk-neutral measure. In that case, you have to estimate only the parameters of the model under the risk-neutral measure, and you do not need to estimate the market price of risk. So here follows a recipe for inverting the yield curve. Firstly, choose some short rate model involving a set of parameters alpha 1 up to alpha n. For example, the Vasicek model has 3 parameters, namely kappa, mu and sigma. The Q dynamics of the short rate are then given in the following form, depending on the parameters alpha. If we model directly under the risk-neutral world, then the market price of risk is 0, and therefore the term structure PDE takes the following form, with the usual terminal condition. We can solve this to obtain theoretical model prices, where the price of the zero coupon bond depends on the parameters that we have chosen. We then go to the market and observe the actual or empirical term structure of bond prices. So these values P star 0t are the market prices of zero coupon bonds, where we may have had to bootstrap the yield curve in order to obtain these prices. We now would like to choose alpha so that the theoretical prices involving the parameters alpha fit the empirical prices that we see as closely as possible. For example, we could choose some benchmark maturities T1 up to Tn and then compute the values of alpha I which minimize the following expression. In other words, we minimize the sum of the square of the differences between the model prices and the observed empirical prices. This is just an optimization problem. Once we've solved this optimization problem, we will have determined an optimal set of parameters alpha star. With these parameters, we now have the dynamics of the short rate under the risk-neutral measure. Now, ideally, the model prices using the optimal parameters will all be equal to the empirical prices for every t. For time homogeneous models, this implies infinitely many equations, one for each t, in only finitely many unknowns, namely the alpha 1 up to alpha n. For the Vasicek model, for example, we have 3 parameters that need to be determined, but we may have the values of zero coupon bonds going out 30 years. Such a model is usually therefore overdetermined and typically cannot fit the initial term structure of bond prices. But if alpha is an infinite dimensional vector, it may be possible to fit the initial term structure exactly. For example, the time inhomogeneous Ho-Lee model has the following dynamics and can be fitted exactly. Here, the parameter vector alpha is an infinite dimensional vector. Once we've parameterized or calibrated our model, we can then price other interest rate derivatives, for example using Monte Carlo methods or the term structure PDE.